All right, good day. I'm going to do a walkthrough of that ideal apportionment assignment from Friday. So over here on the left is the assignment that we had. I'm asking you to do 3 different apportionments showing how each of the 3 different properties have been violated in different examples. We've got the Jefferson method violating the quota property. We're going to have the Hamilton method violate the house size property. We're going to have the Lowndes method violate the population property. Now, reminder, going back to the other video, the notes from Friday, let me switch over. We had those 3 different properties in there. The quota property is no state gains or loses more seats than a natural quota rounded up or down. So basically nobody gets 2 seats or loses 2 seats or more than that. We have the house size property. When we have a fixed population, no state should lose a seat if the house size is increased. So if the house size goes up, then no state should end up having less than they had previously. And third, the population property. When we have a fixed house size, if a state's population increases while another state's population decreases, the state whose population went up should not have fewer seats, whereas the state whose population decreased should not have more seats as a result. So we need to take into account those 3 items when we're working through this. I'm going to go back. So the very first one is portion a 50-member house using Jefferson's method. Identify where the quota property is violated. So I'm going to go through. Over on the right side, I have all of the populations already entered. This is the Jefferson's method calculator that we all have. We've got a 50-member house, so I'm going to put my numbers in there. Right away, we see, okay, we've got our natural quotas. Natural quotas rounded down. 14, 12, 9, 5, 4, and 2. We have a total of 46 currently allocated. We need 50 seats. So Jefferson's method is a divisor method. We're going to go through and change our modified divisor until Jefferson comes up correctly. So 1001 gives us 46. We need to drop that because we need more seats. If we need more seats, we need to reduce our divisor. I'm just going to guess 900. 900 gives us 54. That's too many. That's, let's say, halfway in between there. I needed 4 seats. I got 4 too many. So 950 gives us 48 seats. So we need more seats still. I'm going to drop that number. 925. Too many seats. So 950 was not enough. 925 was too many. How about 935? Not enough. So somewhere in between 925 and 935. 930, not enough. 927. There's a Jefferson divisor. Got that. I have my correct allocation. So over on the left side, I'm trying to use this assignment to help us kind of see what's happening. The initial allocation, I'm going to copy these numbers over to my spot. Our initial allocation, we have 14, 12, 9, 5, 4, and 2. We had a total of 46. Our final outcome that we had, we ended up with 16, 14, 9, 5, 4, and 2. So we had 46, we needed 50, we've got a divisor of 927. So here's where, identify where the quota property is violated. Going back to my notes, the quota property, no state gains or loses more seats than the natural quota rounded up or rounded down. So our natural quota rounded down was 14. Oh, this state gained +2. That's a violation. So it was at 14, it went up to 16. They gained +2. That is a violation of the quota property. 12 to 14, they also gained 2. So that was at 12, it gained 2, it's now up to 14. 9 went to 9, 5 stayed at 5, 4 went to 4, and 2 went to 2. So there were 4 seats to give out. Those 4 went to only 2 different states. That is our violation of the quota property. So that's what I'm asking you to find in there. Next up, we're going to use Hamilton's method, and we're going to show where the house size property is violated. So we're going to do this twice, once with 24 seats, once with 25 seats. Reminder, our house size property, our population is fixed. No state should lose a seat if the house size is increased. Over to the right, I'm going to go back to my Hamilton setup here, calculator. I've got my populations already entered. Check those. We have initially 24 seats. We have my natural quotas there. Our initial allocation is 22. We need 24 seats. So who gets the additional ones? We look at the highest decimals. 7.3, 0.4, 0.42, 0.71. That goes to 3. 0.42 goes up to 4. Those were the extra 2, so that says 4, 6, and 7. All right. So state E had a decimal of 2.7. That is the highest, so that gets rounded up to 3. 3.42 was the second highest. That gets rounded from 3 up to 4, so we've got a total of 24 seats. I'm going to take those numbers and put them in there. So we have a total of 24 seats. We're going to do this now instead with 25 seats. So I'm going to change my house size to 25. That changes all of the natural quotas. Natural quotas rounded down. We still have 22 seats assigned here. So we have 22. We need 25. We need 3 more. So the highest decimal, 6.9, 6.7, 2.2, 5.7, 8.2. So 8.2 is the highest. That goes up from 2 to 3. 0.69 is the next highest. That goes up from 7 to 8. And 6.7 goes from 6 to 7. The others stay the same. We've got 25. So now, take those numbers, put them over. That's our final Hamilton allocation. We've got 25. So we went from 24 seats to 25 seats. We increased the house size. What happened was State A, they went up a seat. State B went up a seat. State C stayed the same. State E stayed the same. State D, all right, there is more stuff going out here. They went from, ooh, that's hard to see. Just highlight it in blue. They went from 4 seats down to 3 seats. So what happened was their decimal was just not enough, and another state actually bumped them out of the running for an additional seat. This was the problem with what's known as the Alabama paradox in 1880, when all of a sudden New Mexico was a brand new state, and Alabama ended up losing a seat to Illinois. It's just the way the decimals work out, the size of the population. It ends up helping you more than, it's not just a straight up, the quotients do not change at the same rate based upon the divisees, the initial values by which we're dividing the state population. So this, it was at 4, it went down to 3. The house size property, take another look at that. No state should lose a seat if the house size is increased. State D lost a seat. That's our violation. All right. Third one, now we're going to use the Lowndes method. We're going to use the Lowndes method to show the population property is violated. So I'm going to go back to my calculator. I've got this set up twice. What I did was I copied the entire thing over again, and I changed the population, so all of my formulas stayed in check there. That's enough to see everything except for the natural divisor. So at first, we have our total population. We're doing this with 23 seats. Put in 23, get all my calculations. We have our initial allocation is 21 for Lowndes. Now Lowndes was the relative fractional part. Round down, determine the relative fractional part. We have 21, we need 23, so we need 2 more. So we look at the largest relative fractional parts. We have nobody at 0 at the start. 0.3, 0.09, 0.05, 0.09. So 0.3 is the largest. That goes from 1 up to 2. We have 0.099, 0.098. 0.099 is larger, so that goes from 3 up to 4. Those are the 2 seats that we gained. The others stay the same. We've got a total of 23. So those values over to the left, that is our old allocation. We have 23 seats. We were at 10, 7, 4, and 2. Now we're trying to show the population property is violated. Population property, nope, wrong one. House size is fixed. No state whose population increases. So we're looking for which states have a population increasing, loses a seat to a state whose population decreases. So we were at 11,167. We are down to 11,160. 7536, 7536, that stayed the same. 3356, 3360, that one increases. 1332, 1200, that one decreases. I'm looking at state C here because I know state C increases. Let's see what happens with that. So we're going to change the populations. I just have the same thing done again over here on the right. Our house size is 23. 23 is a house size. Initially, with those changing populations, we have 22 seats, so we still need one more now. We're assigning one less than before. We have 22, we need 23. I'm going to look for the largest relative fractional part, so 0.18, 0.10, 0.06, 0.00, that 0.18, still the largest. So that goes up to 2. All the others stay the same. So we have 11,732. We have our total of 23. Now let's look at the numbers here. State C had 4 seats, went down to 3 seats. That's the problem. Their population increases. And let's look. State A decreases. They went from 10 to 11. State D stayed at 2. But here's the problem. State C combined with State A. State C, get rid of that, talk about it. State C, their population increased, they lost a seat. State A, their population decreased, they gained a seat. That's the violation of the population property. So going back, no state whose population increases loses a seat to a state whose population decreases. There was the flip. State C, their seat went up to State A. That's the violation of the population property. That's what we're looking for. So we've got 3 more today. I switched it up. We're going to be using Webster's method for the quota property to see how that violates. We're going to be using Lowndes' method for the house size property, and we're going to use Hamilton's method for the population property. That's what I'm asking you to do today. Good luck.